All right, hello. Today we're going to look at electrochemistry. This is Unit 11, Lesson 4. So what we want to be able to do is predict the spontaneity of redox reactions, which is basically saying, will it happen on its own, or do we need to provide power to get the reaction to go? Right? A spontaneous reaction, you don't need an energy source for these redox reactions, but for a non-spontaneous redox reaction, you would need an energy source. Okay, we'll get into that in a little bit. Also, we're going to look at voltaic and electrolytic cells. Okay, we'll talk about what those are. We'll label the parts of each, and we'll talk about the direction of electron flow. Okay, a little preview, right? A voltaic cell it's a battery. Okay, it's a battery. All right. So here's the agenda for today. We'll do a quick do now, look at what electrochemical cells are, talk about spontaneous redox reactions. We'll break down the differences and similarities between voltaic and electrolytic cells, which are electrochemical cells. And then we'll do some check for understanding questions. I peppered in a few more of these because I think they're all multiple choice this week, or this lesson. Okay, so here's a little do now. Go ahead, pause, try this out. Okay, so what do you know about batteries? Well, probably what most people know, right? They power electronics, right? Maybe you said they hold charge, or they have energy, or they store energy. Yeah, so in a battery, right, basically when you charge a battery, it's an electrolytic cell, right? You're putting energy in, you're reversing a redox reaction, which is non-spontaneous, right? Because you need to put power in. And then when you put your battery into your remote or your controller, whatever it is, right? Then the redox reaction, the spontaneous redox reaction happens, and there's electron flow, which is what electricity is. And then that electron flow is able to power the device that it's in. And that would be considered a voltaic cell, okay? Because voltaic cells, we'll see, are spontaneous. Okay, so a little bit of review here, right? Given this equation, what is the total number of moles of electrons lost by the copper as it completely reacts with 8 moles of nitric acid? Okay, this is nitric acid, so we're talking about copper. So we want to quickly know, right? Get my pen here. Right, so copper here has an oxidation state of 0. Okay, and then copper here, right? We got to figure out the oxidation state. So remember, the trick for ionic compounds is that the ions, the oxidation state is the same as the charge. So NO3 is a polyatomic ion with a -1 charge. You can look that up in your table of polyatomic ions in your reference tables. And there's 2 of them for a total of a -2 charge. So to balance that out, copper must be +2. So the oxidation state is +2. Okay, so each copper atom, right, loses 2 moles of electrons. Okay, but there are 3 moles of copper atoms, right? So each mole of copper loses 2 moles because it goes from 0 to 2 plus. If we write that out, right? Well, you can see that, right? Going from 0 to 2 plus, it means you lost 2 electrons. Okay, so 1 mole of copper would lose 2 moles of electrons. But in this equation, this balanced equation, right, we have 3 moles of copper. So it's really 3 times the 2 moles of electrons to get 6. Okay, so tricky, tricky stuff. Really, what you got to first thing you got to do, right, is come up with how many moles of electrons are lost by 1 mole of copper. And we can write that equation. Let's see how fast I can do this. Copper, right, with a 0 charge, no charge, goes to copper with a 2 plus charge. Cu, and when it's a charge, right, we write 2 plus, which means it lost 2 electrons, right? And remember, these coefficients, 1 mole of copper loses 2 moles of electrons. So 3 moles of copper would lose 6 moles of electrons, which is why the answer is 6. Okay, so this one probably is a little tricky. This is definitely the most difficult task in this unit. So I would probably focus on this for review when I put out the assessment coming up on Tuesday. Okay, so let's talk about electrochemical cells. So an electrochemical cell is a cell where redox occurs, where a redox reaction occurs. Okay. Every electrochemical cell has two electrodes. An electrode is just the site of either oxidation or reduction. So at one electrode, oxidation is occurring. At the other electrode, reduction is occurring. And we give these electrodes different names so we know what's happening. Okay, one is called the anode and one's called the cathode. All right, the anode is the site of oxidation and the cathode is the site of reduction. And here's how you remember that. Red cat and an ox. Reduction, cathode, anode, oxidation. So picture this, right? Something that psychology tells us. If visual images are very easy to remember. So if you literally right now close your eyes and picture a red cat, like a bright red cat, sitting on top of an ox. Okay, if you picture that, right? Every time you have to remember which is which, picture that like, okay, it's a red cat on an ox. Oh, right, reduction, cathode, anode, oxidation. Okay, that's how you can remember that. Keep that straight. Electrons will always flow from the anode to the cathode, no matter what. Okay, always. And the way I remember that is it's in alphabetical order, right? It flows in alphabetical order. So anode to cathode, A to C, right? That's how you can remember the direction of electron flow. Okay, I'm going to keep going here, but remember, you can always pause, rewind, watch it again, take some notes, do what you got to do. So the question is, right, if you have two electrodes made of different metals, how can you tell which one is oxidized and which one is reduced? Or even how could you predict before you even do it, right? You could probably tell because the one that gets oxidized might change color, right? You might see new compounds being formed. But let's go with the prediction, right? How do we know? If I have two metals, how do I know which one's going to get oxidized and which one's going to get reduced? So we need table J, right? We've used this before when we looked at acids and bases, right? Remember, anything above H2 reacts with an acid because it's more active, and anything below H2 didn't react, right? So this is the activity series. Essentially, the more active you are, the easier it is to lose electrons. So lithium cannot hold on to its electrons, whereas gold's pretty good, okay, at holding on its electrons. So what that means is, right, remember, oxidation is the loss of electrons. So if you have two metals, the one that's higher up on this activity series is more easily going to lose its electrons. Therefore, that's the element that gets oxidized, which is the loss of electrons. Okay, and then the element, whatever element is further down, is the one that's going to get reduced because it doesn't lose its electrons so easily. Okay, so the one that's highest up, a metal higher on table J, that's oxidation. The lower one is reduction. All right, so let's practice a few of these. Okay, so I'm going to give a couple of elements, and you're going to want to state which one will oxidize and which one will reduce, and then state which one would be the anode and which is the cathode in an electrolytic cell, or sorry, an electrochemical cell. Okay, so, and you can pause as I do each one of these in between each individual one. So calcium and iron, pause, unpause. So I'm looking for these in the periodic table, or in the activity series. Calcium's here, Ca, and iron is Fe. So calcium is going to get oxidized. I don't know where the next one's going to pop up. Okay, calcium's going to get oxidized, and iron is going to get reduced. Oh boy. Okay, and it's also asking us what's the anode, what's the cathode. Remember, red cat, so reduction happens at the cathode, and that means an ox, right? The anode is oxidation. So calcium, if we made a battery out of calcium and iron, the calcium would be the anode. It would lose electrons because it gets oxidized. It would go to the iron, which is the cathode, where the iron would gain them and get reduced. Okay, let's keep going. So silver and nickel. Go ahead and pause. Let down, pause me. Silver is Ag. way down here. This is probably going to be reduction, right? And then nickel, yep, nickel's above it. Still, nickel's not very active, but it's more active than silver, okay? So the more active nickel is going to be oxidized, and silver is going to get reduced. Wish I had better handwriting with this thing. It's very difficult. So again, right, oxidation is always the anode, anox, and reduction is always at the cathode. So in this battery, if we made it out of silver and nickel, right, the nickel would get oxidized, lose its electrons, it'd be the anode, and the electrons would go over to silver at the cathode, and it would get reduced. Okay, a couple more examples. I think you're getting it, though. Magnesium and lead. So Mg and Pb. Lead is Pb. Magnesium, Mg, up here, and lead down here, Pb. Magnesium is going to get oxidized because it's higher up on the table. So magnesium gets oxidized, which means it's the anode, right? Anox. And lead gets reduced because it's further down, which means it's the cathode. Whew. Very hard to write. Okay, one last example, copper and silver. All right, so copper is Cu, silver is Ag, pretty close, but copper's on top, therefore the copper in this case would get oxidized. And oxidation occurs at the anode. And silver would get reduced. And reduction occurs at the cathode. Okay? Boom. That's not cut, that's cat. Okay. All right. So hopefully that makes sense. Pretty straightforward. The one on top gets oxidized, and it's the anode. The one on the bottom gets reduced. It's the cathode. Okay. So we're going to use this in a bit here. So how do we know if a reaction is spontaneous? A redox reaction is spontaneous. So a redox reaction will be spontaneous if the appropriate element is oxidized and the appropriate element is reduced according to table J. Okay, so back here, right, let's go with copper and silver. If we have a reaction where copper gets oxidized and silver gets reduced, that's spontaneous. If we have a reaction where copper gets reduced and silver gets oxidized, right, which is not what it should be, that's going to be non-spontaneous. Okay, so let's look at some reactions and determine if they are spontaneous. Okay, so we have to assign oxidation numbers. So let's do some quick ones, right? Where's this going? Okay. So elements by themselves are 0, lead is 0, nickel is 0. And remember, this is probably, right, always going to stump you, but here's what you do, okay? It's the charge, right? It's going to be the charge of the ion. So SO4, if you look at your table of your polyatomic ions, let's see, where are those? Here, SO4 is a 2- charge, so nickel must be +2 to balance it out, right? Because there's no charge on the whole compound. Over here, SO4, it's 2- again, so lead in this case must also be +2, right? Right, and in an ionic compound, the ions, the charge is the exact same thing as the oxidation number, okay? So because SO4 is 2-, that means nickel has to be 2+, and the same idea here between SO4 and lead. So if we look here, right, nickel goes from 2+ to 0, which means it got reduced, right? Reduced, oh boy. Okay, and then lead goes from 0 to 2+, which means it got oxidized. Now we have to look at table J to see if that's what was supposed to happen. We have nickel and lead. Didn't we just do this one? No, we didn't. Okay, so we go to our table J. Wait, yeah, no, I didn't include it. Table J, nickel and lead. So nickel is here and lead is below it. So nickel should get oxidized. Is that what happened? No. Nickel should have been the one that got oxidized, right? Look at nickel is above lead, so nickel should get oxidized in a spontaneous reaction, but in this reaction, nickel's getting reduced, therefore non-spontaneous. No, I'm just going to write non because it'll take me 6 years to finish that word. Okay, let's try another one. Oh, I should have spaced these out a little bit more, huh? So I'm going to have to erase here. So you can always pause and go back. Okay. Okay. Okay, we got to put in our, and again, you can pause and try this one if you want, right? I always like to start with the elements by themselves. They're always 0, doesn't matter what they are. And again, PO4. What's the charge of PO4? Okay. PO4, come on. PO4 is 3 minus. So that means gold, AU here, has to have a positive 3. Okay. And you can go in, you can put oxidation states on these guys, but they're not going to change because when a polyatomic ion stays together like that, it's not going to get up. It's not breaking apart. Nothing's happening. It's not losing any electrons, which means same case here, right? PO4 is 3 minus, so aluminum has to be plus 3. Okay, so now we look. What does gold do? Gold goes from 3 plus down to 0. It gets reduced to 0. I have a feeling that's going to be what it should do because I think gold is on the very bottom of that activity series, right? And then aluminum goes from 0 to plus 3. It gets oxidized. Okay, oxidized, 0 to plus 3. So gold's getting reduced, gold and aluminum. Let's check it out on our table. Yep, gold's at the bottom, aluminum is way up here. So aluminum should be the one getting oxidized. That's what happened. This is spontaneous. S-P-O-N, spawn. I'm going to stop right there. Okay, a couple more. And again, I got to erase the some of this here just to make space. Okay. Okay. Again, these are very similar, right? So zeros for these guys because they're by themselves. CO3. I don't know what the charge of that is. It's probably like 2 minus or something. CO3, yep, 2 minus. So if this is 2 minus, SR must be have a plus 2 oxidation state, a 2 plus charge, and a plus 2 oxidation state. And the same deal here, right? I made these pretty easy. So tin, SN is tin, must have a plus 2 oxidation state. Okay, so I'm not going to write. Let's see if we can just do this without me writing the arrows. SR, strontium, goes from 2 plus to 0. It gets reduced. And tin gets oxidized, goes from 0 to 2 plus. Remember, the number that gets reduced is reduction. That's what reduction is talking about. Okay, so strontium gets reduced, tin gets oxidized. Let's see if that's how it's supposed to be. Strontium gets reduced, tin gets oxidized. So tin is way down here, strontium's way up there. So strontium should be the one that gets oxidized. Strontium got reduced, so this is non-spontaneous. Okay, it doesn't match up. Okay, last one. Okay, let's put in our oxidation states. Copper's by itself, iron's by itself. OH, I remember, it's on the table of polyatomic ions, but OH has a -1 charge. So iron here has a +1 charge, so the oxidation state is +1. Again, -1, that means copper is +1, which means the oxidation state is +1. So here we have iron going from +1 to 0, getting reduced. Copper goes from 0 to +1, getting oxidized. So iron's getting reduced and copper's getting oxidized. So Fe and Cu. So iron should be getting oxidized. But here iron gets reduced, therefore non-spontaneous. Okay. Right, so if you want steps for that, right, you write your oxidation numbers, figure out what gets oxidized and what gets reduced, and then you look at table J to see if that's what should have happened, right? The element on top, whatever it is, the one higher up, should be the one getting oxidized. If it is in the equation, then it's spontaneous. If it's backwards, if it's not, then it's non-spontaneous. Okay, So this reaction will happen naturally, the spontaneous one. A, C, and D, these three reactions, you would have to apply electricity to get them to do this reaction. These reactions won't just happen on their own. You would have to apply electricity. Actually, if you reversed these three reactions, they'd be spontaneous. Okay, so this is all kind of leading up to this. We have two types of electrochemical cells, which remember, it's a cell where a redox reaction occurs. Okay, so we have voltaic, which releases energy in a way, right? You could power stuff with a voltaic cell. And electrolytic requires energy. Okay, so let's look at the similarities and differences. So voltaic reaction occurs spontaneously, right? If it's powering something, it occurs spontaneously. We don't need to put a power source in. Okay, a voltaic cell, the anode is negative, kind of like it should be. Okay, right? Remember, anions are negative ions, and cations are positive. The cathode is positive. Chemical energy is converted into electrical energy. Think about a battery, right? A battery is a chemical reaction, a redox reaction that powers stuff. It's converted into electrical energy. And specifically in a voltaic cell, there's a salt bridge that allows for the flow of ions. Okay, it allows ions to flow between the two halves of the cell. All right. So there's a salt bridge in a voltaic. There's no salt bridge in electrolytic. That's one way to tell them apart, among others. Electrons always flow from the anode to the cathode. Okay, that's always true, even for the electrolytic cell. So the electrolytic cell reaction is non-spontaneous. How do we know? I mean, look, it requires electricity, right? This one is producing electricity. This one requires it, so non-spontaneous. And the anode and cathode are backwards. Okay, the anode here is actually positive, which is kind of strange, and the cathode is negative. Okay, so it's backwards. In this case, the energy conversion is also backwards. We're using electrical energy to make a chemical change. Okay, so electrical energy is converted into chemical energy. It requires a power source, right? Because you need electrical energy. As always, electrons are still flowing from the anode to the cathode. Looks weird though, because look, electrons are leaving the positive thing and they're going toward the negative thing. Yeah, they don't do that on their own. That's why you need a power source. You need to force it, essentially. Okay? So, this is a lot of information on this slide. I would pause here and just kind of take notes, study this stuff. Voltaic is spontaneous, anode's negative, cathode positive, chemical to electrical energy, and there's a salt bridge. Electrolytic is non-spontaneous, the anode is positive and the cathode is negative, all these are backwards, right? Electrical is converted to chemical. So all these top 4 points, they're all opposites, voltaic and electrolytic, right? Electrolytic, there's no salt bridge, it needs a power source. In both cases, electrons are flowing from the anode to the cathode. Okay, so let's apply this to see if we know what's going on here. Let's check our understanding. So there's actually 2 slides of check for understandings, just because I want to do a few different problems. So go ahead and pause and try these out, and then unpause me. Okay, so number 1 here, or the first one I guess, they're not numbered. Base your answer to the following question on the diagram of the chemical cell shown below. The reaction occurs at 1 atmosphere and 298 K. Okay, so here's our reaction, here's our cell. It says, what happens when the switch is closed? So let's just figure out some stuff about this. So right away, I noticed a salt bridge. I know this is voltaic, right? Because there's a salt bridge. There's no salt bridge in electrolytic. So this is a voltaic cell. So it gave us the reaction here, right? So that means this reaction is spontaneous, okay? Looks like we have zinc going from 0 to 2 plus, getting oxidized, and lead going from 2 plus down to 0, getting reduced. So it's asking, look, if we look at the choices here, it's asking about, well, first of all, we just said zinc's being oxidized, right? So it can't be A, and it can't be D. Okay, because if zinc's being oxidized, lead can't be oxidized, and this literally says the opposite. So it's got to be B or C. We've already narrowed it down. Now it's about determining which way are the electrons flowing. Remember, electrons always flow, alphabetical order, from the anode to the cathode. And in a voltaic cell, right? In any cell, excuse me, the anode, remember red cat and anox, reduction is at the cathode. So this must be the cathode, right? Because lead gets reduced. So this is the cathode. And anox, anode is where oxidation happens. So zinc is being oxidized, so this must be the anode. Okay. And electrons always flow from the anode to the cathode, so they must be going this way. Okay. Electrons have to be flowing from the anode to the cathode. And these are electrons, our little electron buddies. E minus, that's what that's supposed to say. Hopefully you can read that. E minus, that's pretty good, E. Okay, so B says lead is reduced, yes, and electrons flow to the zinc electrode. No. Okay, so it's got to be C, but let's read it. Zinc is oxidized. Yep, sure is. Goes from 0 to +2. And electrons flow to the lead. Yes, there's our answer. Okay, so, I mean, there's a lot of stuff to know there, right? We gave us the equation, luckily, right? That was nice of them, okay? We noticed it was a salt bridge, so we knew it was a voltaic cell. It also has this voltmeter. That's kind of a giveaway. We determined that if the zinc is being oxidized in the equation, then the zinc must be the anode. If the lead is being reduced in the equation, then lead must be the cathode. Okay? And electrons always flow from the anode to the cathode, so the only answer that makes any sense is C. Okay, let's look at this guy. So right away, before I even read this, right? Power source, this is an electrolytic. I already started, gotta finish. Okay. Electrolytic, there we go. So I know this is electrolytic, okay? Which statement best describes the key? So this thing, okay? Let's see, lots of stuff going on. This looks pretty strange, right? We got silver, we got a key. I don't even know what it's made of. Doesn't tell me. So it's asking about if the key is going to be a cathode or an anode. So let's start there. So look at the direction of electron flow. You have to use all the information they give you in these little diagrams. So if electrons always flow from the anode, so the anode must be over here, to the cathode, that means the key must be the cathode, because that's where the electrons are flowing. So we can get rid of C and D, because those say it's the anode. We're talking about the key here. So now we got to know, okay, is the key negative or positive? Well, remember, in an electrolytic cell, the cathode is negative. Okay, it's kind of backwards, right, from this. Over here, the cathode would have been positive because it's voltaic, and the anode is negative, but here, the cathode is negative and the anode is positive because it's an electrolytic and it's backwards. All right, so that means the answer must be A. Acts as the cathode and is negative. Okay, that's why it requires a power source, right? Electrons don't like to move toward negative things, but if you provide power, you force them to, right? They won't do it on their own. Right, and what this is illustrating is called electroplating. If you took a key and you put it in a system like this, the silver ions dissolved in the water here would actually, because you're adding electrons to the key, the positive silver would stick to the key, and you could coat this key in silver. This is actually how they plate things, right? So pretty interesting. It's called electroplating. Look it up if you're interested. I'm sure there's a million YouTube videos on it because it happens pretty quick, and sometimes it's really pretty. It's cool to watch, cool chemical reaction. And that's electroplating. Check it out. All right, let's do a few more. I got 1, 2, I'll give you 4 more here. So pause, why don't you pause and try all 4, unpause me, and I will go through them. Okay, so number 1, we got a diagram, shows a key being plated with copper in an electrolytic cell. Yep, definitely electrolytic, it told us, but right, how do we know? We see the battery, okay? Given the reduction reaction for this cell, so the reduction, so it's telling us, right, the copper is being reduced, right, gaining electrons. This reduction occurs at, let's see, okay, we have A and B. So let's think about this, right? It's electrolytic. Reduction always occurs at red cat. So it's got to be a cathode. So let's get rid of A and C, right? Reduction's at the cathode. And now we got to figure out which one of these is the cathode. So in an electrolytic cell, the cathode is negative. So let's follow the negative lead. Boom. It's got to be the key. Okay? Because it's negative. Right? Cathode's negative. The anode is positive in an electrolytic cell. All right? So the answer here has to be, right, reduction occurs at A, which is the cathode. Okay? Got to use all the tools here, everything it gives you. 2, which energy conversion occurs in an operating voltaic cell? So remember, voltaic cell, you can power stuff with it. So electricity is going to come out. And what it is you're turning a chemical energy into electrical energy, right? The chemical reaction, the redox reaction, produces electrons that you can then use to power stuff. So it's chemical to electrical in a voltaic cell. All right, and which energy transformation occurs in electrolytic? Electrolytic literally requires a battery, right? You have to take electrical energy and turn it into chemical energy. So that means this is going to be B. Okay, and now we got last diagram here. Before I even look into it, look at this salt bridge. It's voltaic. It's got to be voltaic. Also, they usually put this little V in here. Gives it away too. But the salt bridge is key, okay? So this is our voltaic cell. Let's see. What's it asking? What occurs when the switch is closed? So let's just break down this thing real quick, okay? So we have zinc and copper, okay? And, it's not telling us, didn't give us the equation like it did that last time. So we have zinc all the way up here and copper down here. And remember, it's voltaic, so it has to be spontaneous. So if it's spontaneous, that means zinc must be being oxidized because it's higher up on the activity series. So zinc, this is the site of oxidation. Oxidation, and this must be, that means this copper gets reduced. Okay, and we know red cat and an ox, right? So reduction at the cathode. Oops, I'm writing reduction again. Red cat, this must be the cathode. Okay, and ox, this must be the anode. Okay, and it's going to ask about, okay, so let's look at these two. These are probably wrong, right? So zinc is reduced. Nope, zinc's oxidized. Copper is oxidized. Nope, copper is reduced. Boom. Now we got to look at electron flow. Electrons always flow from the anode to the cathode. So anode to cathode, that's what we're looking at. Okay, so it's going this way, anode to cathode, or from the zinc to the copper, which means the answer is D. Electrons flow from zinc to copper. Okay, lots of little pieces of information in this. Hopefully all the example problems helped. Your homework looks exactly like these. I think you might even see some of the exact same problems. So go ahead and try this out. Remember office hours. So officially, I know I updated a few things today, or I guess yesterday for you guys. Tuesdays and Fridays when the new lessons come out, they should come out at 9. if I remember to post them. And office hours is open to anybody, right? Multiple people can join the same session. And then the other days of the week, so Monday, Wednesday, Thursday, office hours will be by appointment. So if you'd like to set up a one-on-one meeting, a 15-minute meeting with me and go over stuff one-on-one, you can do that. And just go to Google Classroom. You'll find the link for that, and you'll just click the appointment slot. It'll sign you right up. It'll make a private Google Meet for us. Okay, so go ahead and jump on that homework. It's the last lesson in the unit. Cool. I'll see you guys later.